The last video you watched most likely talked about this page, page 4 on the new Class 17 handout, going over allylic halogenation. Why don't we apply some of these concepts to these 4 reactions? I'm going to try to make the exam problem either identical to this, if it's about allylic halogenation, or very similar to this. For the following allylic halogenations, draw all the possible products. If a mixture is made, circle the major products. All of these use NBS. That's the only way that I want us to use or want us to do a allylic halogenation reaction. Let me do, okay, I'm going to do this a little bit fast, at least the first 2. And then I'll slow down for the last 2, which are a little bit trickier. Okay, I see 2 allylic carbons, but no matter which one I use, I'll get the same products. So I'll call this allylic carbon A, same as allylic carbon A. I get I get an initial radical, intermediate, which is, I'll use this one on top. And then with the resonance, I get this shift, that. Okay, so that's pretty fast. Hopefully with practice you'll be just as fast. If you want to, I'll draw the mechanism arrows once. Right? So you make a double bond on the wall on the right, and the radical now goes on the carbon that lost a bond, which is this methyl radical. And your 2 products are this. Let me draw this one first. We'll assess whether they are identical or not, and if they're not identical, hopefully we can decide who is the major product. Okay, they're not identical, that's for sure. And this is the tri-substituted alkene, and the one on the left is di-substituted. Just a note, both are allylic bromides, right? Allylic. I think one of the more common mistakes is that just because you draw something that's allylic doesn't mean it's a product. It has to literally come from a radical that you know is being made. So for instance, this one here. Let's say you knew the double bond shifted, but you draw the bromine here at this allylic position. Well, that didn't come from a radical that we see. Right? There was no radical where we had the double bond here and the radical here. You have to draw the products that are coming from the 2 radicals. Okay? The other thing is, it's kind of a shortcut. Just because the radicals have different stabilities, you can't use the stabilities of the radicals to determine the stability of the products. You're only looking at the alkenes, the double bond. So again, just as a reminder, you're picking the more stable CC double bond, or the more stable alkene. Okay, regardless of the stabilities of your radicals. Okay, the next one. Okay, going a little bit fast still. These are our 2 allylic radicals, and they are different. We'll call this A, and we'll call this B. But just like on page 4, we had an example where one of the allylic carbons has no hydrogens. Therefore, you cannot make a radical on that carbon because there's no hydrogen to abstract. I'm using the word abstract because that's the proper term for removing a hydrogen in a radical mechanism. So we see hydrogen abstraction in our mechanism for radical halogenation, reaction 18A. I know this is reaction 18B, but we are still forming radicals, and you still need that hydrogen to remove. Let's draw the intermediates, the radical intermediates, and we're using B, not A. So there's your first radical, and with resonance you get a second radical. Okay, I'm not going to draw the mechanism arrows this time. Right there. That's the carbon that was naked, the one up here at the 12 o'clock position. Okay, our two products are this. BR. And it will always be BR because we're using NBS. There is no chlorine equivalent. So we're making allylic bromides. So it goes here. Okay. I always hold my breath because I'm really hoping there is a major product. And this one here is tri-substituted. Right, up here also, tri-substituted. This one was di. This one also is di-substituted. Okay. How can this get more complicated? Anytime we had two different allylic carbons, I made it simple by making one of them not have a hydrogen. And I think we saw that on the previous page where we have A and B. See, A and B, but B has no hydrogen. But what if B had a hydrogen? What if both allylic carbons have a hydrogen? It gets complicated now because we're going to have multiple products, more than two in many cases. Allylic A, allylic B. So yes, we have to do it for both, for A. Okay. For this one, I am going to draw the intermediates. For the last one, I'm going to try not to. Okay? So let's make sure we know how to do it with seeing the intermediates. This takes practice. I am going fast, but just to show you that eventually you could go this fast as well. See, the initial radical for A, literally, you just put the bromine where the initial radical is, right here. So I really don't need to draw this. I know that one of my products, the bromine, will be on this carbon. And I'm going to visualize this double bond shifting, like in resonance, and the new position now will be here. I'm trying to draw the products, or trying to think about drawing the products without having to draw the intermediates, radicals. Okay, but I'll do it again here. So this is for radical B, and we have this one first. Where's B? B is at the very end, right there. And the resonance, you shift the double bond to the right and you get the new radical there. Okay. Our two products now coming from radical B is this.
On versus Toyota RAV4. Look what Sun has.
Yikes. And then this one here. Okay. Now, how do we choose the major product? I'm going to hold steady to this rule that you're going to choose the major product from each radical. So choose a major, hope this works, product from each radical. And when I say radical, I'm talking about this, to me, is one radical. It's a combination of these two. So I'm choosing between these two for set A, these two for set B. Let's look at set A. Okay, thank goodness. We have something that's tri-substituted. The other one's di. Tri, di. For set B, I have here di, and I here have mono. Okay, this could get tricky if you're not understanding what I'm saying here. I'm not asking you to compare all four and pick the best one out of the four. I'm asking you for each set of two, pick the best one. And yeah, so you'll have some instances where I'll pick this di substituted, but not this one. Because from radical B, this is the major product. And we're going to do it that way. There are other ways to pick the major products, but I think this is the easiest. Some of the harder ways will say, circle the major one coming from the more reactive radical. I do not want to go down that path, not right now at least. So for allylic halogenations, I am not going to ask you which radical is more reactive. Okay? Just pick, when you have your four products, look at set A, and pick the best one there. Look at set B and pick the best one there. Okay. The last one, let's try without drawing the radical intermediates. Now, we have four allylic carbons, here, and here, and here, and here. But the thing is, this one would give me the same products as this one, because of symmetry, plane of symmetry, and this one would be the same as this one. And so I am drawing only four products, two from radical A and two from radical B. Radical A would be this. Just draw it as is, and there's a radical right here at the 12 o'clock position. That's where the bromine goes. Now, imagine this not there, and there's a radical right here. You shift the double bond over, the new radical will be here. Can you remember that? You shifted the double bond to the left, and the new radical now is on this carbon that's naked right here, and that's where the bromine goes. That is coming from set A. From set B, we have, what do we have? You draw it as is, and I'm going to use this B at the bottom, this one right here. So that's where I have that. Let me draw the bromine a little bit better. Plus, okay, what are we visualizing? This double bond shifting, this carbon being the naked one, the one on the ring. Okay, this one shifting here, naked. Okay, circle the major product from A. We have a tetra. This is our first tetra substituted. And the major product from B, we have a tri-substituted. So I know again that this is tri-substituted, but you're comparing these two only to each other and these two only to each other. All right, that is how your exam problem on allylic halogenations will look like. I'm going to keep it the same wording. What this also means is that I will set this off in its own section. I'm not going to scramble it with the other reactions that you are learning. I will literally say, for the following allylic halogenations. This is the same problem, not the same molecules, but the same wording in the class 18As, so you get used to seeing that. That is the last page on this new class 17 handout, page number 5.